Today we're going to be going over the Monte Carlo Python simulation question. I hope to help you guys visually understand what's happening behind the scenes and some real world use cases like how Wall Street uses it to make better trading algorithms and how video games use it to decide different spawn rates of different loots. All right, so let's get started. We're going to be taking on this question with a little bit of a twist. We're going to try to one pieceify it. So let's imagine that you're on the Grand Line on a brand new pirate quest. You're just starting off your journey, and in front of you there are 3 closed pirate treasure chests. Behind pirate chest number 1 is a marine tracker Den Den Moshi, and what this does, it reports your exact location to the Navy. Behind pirate chest number 2 is absolute danger. It's a 1v1 fight against Admiral Fleet Akainu. You're gonna end up just like Ace. And behind pirate chest number 3, well, that's the ultimate grand prize. We got Kaido's mythical Zoan dragon fruit. All right, so let's say in this scenario, Shanks has given you the choice of picking between these 3 chests. Now, the only thing is that you yourself don't know what is behind the doors or the chests. Shanks, on the other hand, does know what is behind them. So he lets you pick your choice first. You go with, let's say, choice number 2. You've picked the absolute worst one. You've picked Admiral Akainu. Now Shanks turns to you and he asks you, would you like me to eliminate one of the doors? One of the doors that definitely does not hold the mythical Zoan fruit. Well, you of course say yes. And now you've got 2 choices. He asks you, do you want to stick with pirate chest number 2? Or do you want to swap to pirate chest number 3? Now, most developers and most mathematicians, I guess most people intuitively would fall into the trap. They would stick with their guns and not swap doors. This is the completely wrong approach. Swapping chests to the other third chest actually doubles your expected win rate from just 33% to 66%. Now, how does this actually work? Why does this work? Shouldn't it still just be 33%? Well, I'm going to use the Monte Carlo Python simulation to prove why this works to you guys throughout this video. All right, so now let's actually analyze the mathematical probability before we jump straight into the Python code. So if we let C be the random variable for the devil fruit index, and we let X be our initial pick, then the probability that your initial pick is correct is actually 1/3, or about 33.3%. That means that the probability that the devil fruit is behind one of the other 2 chests is 2/3, or roughly 66.6%. All right, but here's the key constraint that tricks everyone up. Shanks' reveal is conditional. Shanks cannot open your own selected chest, and Shanks cannot reveal the devil fruit. So this means when Shanks decides to eliminate chest number 1, the probability does not collapse to 50-50. Because Shanks was forced to pick a non-winning chest, the entire 2/3 probability from the remaining unchosen chests condenses exclusively into pirate chest number 3. If you stay with chest 1, your win rate stays at 1/3. And if you swap to chest 3, your win rate doubles to 2/3. All right, so with this actually cleared up, let's jump right into the Python code line by line. So line 1, we're going to import Python's built-in random module. Then we're going to go straight to line 3 and define our main function, simulate Monty Hall. Notice we use Python type hints, end games as an integer, and switch strategy as a boolean, returning a float. And then on line 4, we initialize wins is equal to 0 to track successful devil fruit picks. Then on line 5, we define our prizes list, the Den Den Mushi at index 0, Admiral Akainu at 1, and Kaido's devil fruit at index 2. All right, so now jumping to line number 8, we actually start our simulation loop. We do for underscore in range of n underscore games. And we use an underscore because we don't need the nested loop index variable. On line 10, we set doors equal to prizes.copy, which creates a shallow copy of our prize array so we don't mutate the original master list. Then we jump straight to line number 11, which runs random.shuffle on doors. Under the hood, CPython uses Fisher-Yates algorithm to permute our list into O3 linear time. Then we jump straight onto line 13, which represents your pick. Player choice is equal to random randint 0, 2. This samples a discrete uniform integer across indices 0, 1, and 2. Alright, so let's look closely at lines 15 through 18. This list comprehension is exactly where we code Shakes's constraint. So we start off with host reveals is equal to I for I in the range of 3 if I is not equal to player choice and doors I is not equal to Kaido's devil fruit at index 0. I for I in the range of 3 checks all 3 chest indices. If I is not equal to player choice, which ensures Shanks will never open your chosen chest, and doors I is not equal to Kaido's devil fruit, guarantees Shanks will never reveal the devil fruit. We append 0 to the end to grab the first valid index from the filtered list. Next, we're going to jump straight into line number 20 to check if switch strategy. If true, line 21 runs another list filter to swap your choice to the remaining unchosen, unrevealed chest. Lines 27 and lines 28 evaluate the win condition. If doors, player choice, is equal to Kaido devil fruit, wins plus equals 1, or we increment by 1. Finally, line 30 returns wins divided by n games, giving us our empirical win percentage. When we execute this for 1 million games, staying wins 33.3%, but swapping wins a staggering 66.6%. Our pure Python implementation took about 2.1 seconds to simulate 1 million iterations. Now, 2 seconds might sound fast to an average person, but in computer science and in quantitative finance, 2 seconds is an absolute eternity. If you scale this up to 100 million runs, a pure Python loop takes over 3.5 minutes. On Wall Street or in live game servers, 2 seconds of lag is a complete disaster. You could have just lost millions of dollars or got melted in a match. CPython is slow here because it executes 1 million object allocation, dynamic type checks, and GIL overhead cycles. So we rewrite this using NumPy SIMD vectorization. Alright, so let's look at lines 5 and 6 in our fast implementation. Car doors is equal to numpy.random.int 0, 3, size of n games. Well, this actually allocates a continuous C block of 1,064-bit integers directly in RAM. Here's a mathematical secret on line 12. Swap wins is equal to numpy.sum, player choices is not equal to card doors divided by n games. Because Shanks is forced to reveal a losing chest, swapping wins if and only if your initial choice is wrong. So what do we do instead? Instead of looping item by item, player choices is not equal to card doors, executes across CPU vector registers, evaluating 8 to 16 integers per single clock cycle. Execution time drops down from 2.1 seconds down to 0.009 seconds, a 230 times speedup with 0 memory allocation overhead. Now, why is the Monte Carlo simulation a core requirement for senior software engineers and quantitative data analysts? Well, that answer is very simple. First, quantitative finance and value at risk. Wall Street trading algorithms don't just calculate static stock returns. They run 10 million Monte Carlo random walking simulations with interest and rate spikes, market crashes, geopolitical events, all to compute the maximum expected portfolio loss at a 99% confidence interval. Alright, so where else do we actually use it? Well, secondly, we use it in game engineering and loot drop balancing. Game studios use Monte Carlo simulations to model gotcha drop rates, loot box economies, and matching algorithms across 1 million simulated players. This guarantees balanced game economies before shipping to production. Could you imagine having a game like Blocks Fruits, but instead of having rare fruits, extremely hard to find, everyone just got Kaido's super rare fruit? The game wouldn't even be fun. There would be no real reason to play. This is another awesome use case of the Monte Carlo simulation to make sure your loot that's being dropped onto the floor or picked up by a player isn't completely overpowered and allows you to see what your game would have actually output to the player before shipping it out to production. Alright, so look, whenever you're dealing with crazy probability or complex systems that just completely trick your brain, don't just rely on your gut. You can write a quick Python Monte Carlo simulation, vectorize it with NumPy, and let empirical math prove that truth for you. I put all the full Python code, NumPy benchmarks, and 1P simulation logic in the GitHub repo link in the description below so you can clone it and run it for yourself. If this helped you to actually understand the Monte Carlo Python simulation visually, I hope you drop a like, maybe subscribe to the channel, and I hope to see you guys in the next video.